Okay, shalom. What I will do today is wrap up the ICA topic and connect it also to visual receptive fields, also receptive fields, very briefly receptive fields in other sensory areas, and then just start to tell you perhaps about what we'll do next. So let me start with a reminder about what we did last week. We discussed the Infomax approach to ICA. To independent component analysis. So this is a reminder. We assumed that the ICA problem is defined in the following way. We have some sources which are assumed to be independent. These sources are somehow mixed by a mixing matrix A transpose, and we call the outcome X, and X are the inputs that we are faced with. We want to separate. Our goal is to reconstruct the sources from the inputs. And so the problem is to find a matrix, W transpose, the mixing matrix that will generate a reconstructed input. So far this is just a reminder what is the definition of the problem. The ICA approach, the Infomax approach, is that we suppose that these are non-linearly transformed into some outputs y, where yi is some function of ui, and the approach is to maximize the mutual information between y and x. This is the way I described it last week, but following a question that I was asked after the class, this is the same as the mutual information between y and s. And the reason is that we assume that there is no input noise. So the transformation between s and x is deterministic. And you know that a deterministic transformation does not change the mutual information. So this is because there is no input noise. Okay, so this is the approach. And why does this approach make sense? It makes sense because we know that if we want to, if there's no input noise, this goal is really equivalent to maximizing the entropy of the outputs y. And to maximize the entropy of the outputs y, we know that they need to be uniformly distributed. And so it's essential that this function g is bounded between some minimal values, say between 0 and 1. It's a sigmoidal function. This is really important.
The max of this mutual information is the max of this mutual information? Should be max before?
Yes. Let's do it write it like this.
No, you can also continue to equal the maximizing of the entropy of just one.
Yes, that's true. So we know that if y has maximum, so y is a variable which is bounded, say, between 0 and 1, I mean multidimensional, and we know that if it has maximum entropy, it has to be uniformly distributed, and the different indices needs to be independent. So if we find a solution where y has maximal entropy, it will pick up such a transformation that indeed the yi's will be independent of each other. And so the approach, the idea that we next discussed is that we choose the g. We assume that we know what is the probability distribution of the SI. So if we know that, and we choose the G, and then the idea is that the UIs will be proportional to the SI, so we will choose the nonlinear transformation here such that it will be the cumulative probability distribution of the PIs such that the YIs will be independent. And so, for example, if the P is logistic, then the appropriate form of G is a function that looks like this. It's a cumulative probability distribution of the logistic function. It's a tangent, it's a hyperbolic tangent with some offset. But then, this is G. So this is the P of S, and this will be G of U, the G of U that we will choose. And then what I showed you, what we saw at the end of the class, is that once we formulated this problem like this, we go through all the math. In fact, I didn't go through all the math. Part of the math I skipped, and I told you what is the answer. But we wrote that maximizing this, we wrote that this problem of maximizing this quantity as a maximization of a Lagrangian. And after writing the requirement that the Lagrangian derivative with respect to the W's is 0, we obtained the result that all this, so this is after some work, all this is equivalent to the following requirement. Find W, and in fact it's really equivalent, it's the same thing. Find a W such that Ui, age of Uj is delta Ij, where the function age of U is related to G of U by the following equation. It's minus d to du of log G prime of U. And for a logistic function, for a logistic P, it ends up being simply a hyperbolic tangent. So age of U is hyperbolic tangent of U. Okay, so all this was a reminder. Now I want to make a few comments. The first comment is that this looks quite similar to what we were trying to do when we did PCA. In PCA, we just wanted the UI UJs to be delta Ij, right? But here we have a nonlinearity. And of course, a function like h of U, we can expand it in a Taylor expansion. We can write it, h of U is equal to some alpha, sorry. We can write it as alpha 1 U plus, in principle, alpha 2 U squared over 2. For this particular function, it's an odd function, so there will be alpha 2 will be 0, but let's write it more generally. U2 squared over 2 plus alpha 3 U cubed, what am I doing? U squared, U cubed over 3 factorial, and so on. Just a Taylor expansion. Now, so you see that in some sense, we're doing requiring some nonlinear or higher order correlations to be 0. Now, suppose that our assumption, our underlying assumption is correct, that there are some sources which are independent of each other. Okay? If there are such sources, and we indeed manage to find a transformation that will recover them, then any combination between Ui and the power of Uj, right? Okay, let me write it down. If Ui and Uj are independent, then necessarily for any power, it will be true that ui uj to the power n will be 0 for any n, right? Because then it splits into a product, and the ui's are 0 mean, so the average of ui is 0. And this gives you an important insight on why this method is powerful as a general method for independent component analysis, even if we don't know the P of S. So remember, in my derivation here, I assumed that I know exactly the probability distribution of the S's. And then we went through all this analysis, and we came up with this requirement where H is a very particular function. It was, say, a hyperbolic tangent if I assumed that P of S was logistic. But really, in reality, when we want to separate sources, we often don't know what is the probability distribution. And nevertheless, this method works as a way to separate the sources. The reason that it works is that if indeed there are independent sources, this requirement really will pick up. I mean, it turns out that, I mean, on one hand, if you pick up the independent sources, this ensures that all these correlations will be 0. And it turns out that in most cases, there will be only one solution where this will be true. So this requirement is somehow removing the redundancy that existed in the first order. In the PCA, in the order of PCA, if we just require that ui uj is equal to 0, there are many possible solutions. But if you use the higher order correlations, there is just one solution, and it turns out that it works even if you don't match this function precisely to the probability distribution of the inputs. Okay? Now, in many situations in reality, the assumption that there are sources which are truly independent of each other is just not true. I mean, very often, we have some inputs to our system. Suppose that I put 3 microphones in a room, and I try to separate 3 sources. Maybe, you know, the auditory input that falls on the microphones is not just a linear combination of 3 independent sources. Maybe there are other sources. Maybe they're not completely independent. The people are, say, 3 people are talking with each other, so there will be some correlation between what they're saying. So in those cases, things become more murky. The way I choose this function will affect what outcomes I will get. Okay? But again, as long as I assume that there are independent sources, this is a very powerful and general way to separate them. Yes?
So, if you don't know the initial solutions,
Yes.
and you don't get to this function, so maybe you're saying it will still work, but how can you find W if you don't have the function?
No, so I just use the tangent, hyperbolic tangent. And people use sometimes other functions, but it's really not, it's quite robust to the choice of the function. That's my point. So in the way we derived it, we went from some principle and we obtained this particular function, but it actually turns out that it doesn't matter so much. And this also shows you this so let me just call this high order decorrelation. It also shows you in another way why non-Gaussianity in the inputs was important. Because if the inputs are Gaussian, whichever way you find to make the first order correlations, the ui uj with powers 1, 0, or delta ij, in any way that you will find, and we know that there are many different ways to do it, this will automatically make all the higher powers 0 as well. This is if the inputs are Gaussian. But if the inputs are non-Gaussian, that's no longer true, and the higher order powers remove the redundancy or the degeneracy of the PCA solution. Okay, so I don't want to even to go into this topic. It's more complicated. We assume that they are. Okay? And, yeah. Okay, so another comment. So this was my first comment. A second comment is about another interpretation of the same algorithm. fact, before I mention another interpretation, let's repeat again what was the interpretation of the first algorithm. The interpretation was we go through all these steps, including this nonlinearity, and we want to maximize the information in the wide, which are nonlinear functions of the use. Now let's forget about this step and think directly about the use, which are really what we want to obtain. So just a linear transformation. But let me first write down the Lagrangian that we maximized. So this again, this is the same Lagrangian that we obtained last week. I'm just writing it. Ln G prime of ui. So I just want to look at this Lagrangian and interpret it in a different manner. So I will say the following. This represents the mutual information between the U's and the S's, or the entropies of the U's. This is related just to the U's. It does not involve the nonlinearity. And I will reinterpret this term by, first of all, asking myself, how does this function G prime of U look like? So it turns out that for the logistic case, the function G prime, so again, this is for the logistic, P, G prime of U as a function of U looks like this. It's linear for it's linear for large U. Here it curves up, it curves a little bit. Sorry, this is ln G prime of U. Okay. If you're not convinced, just take this the logistic function, do the log and the derivative and the log, and plot it in MATLAB or in Mathematica. So in some cases where people have been thinking about this algorithm, and we'll talk about it in more detail very soon, this part of the Lagrangian was interpreted in a different manner than what we've done so far. So the idea was we maximize somehow the entropy of the U's, but we have some additional constraint or additional goal in our optimization, and this is given by this term. So we want to make, in addition to the fact that we want to make the entropy of the U's large, we want to make this this term large as well. And this has been interpreted in the literature as a requirement of sparseness. Why? Because if we want this thing to be large, it favors the distributions over the U's that are more centered at the towards the center relative to, say, a Gaussian distribution. Okay? So Gaussian, if you have a Gaussian distribution and you ask what is the average of this quantity, we'll get something. But if you generate a distribution over the U's which is more sharply concentrated near zero, it will give you a larger value of this quantity, given the same variance. And I'm mentioning this because we'll discuss in a few minutes work by Olshausen and Field. Yes. So the fact that we want to make this for each output unit, the U, we think now about the U's as the output units. We want to make this quantity large. Is really some requirement about the distributions of the U's, right? This is the average of the U's, but not just the U's themselves, the U's once we pass them through this function. And it has been interpreted as a requirement or a desire or goal that the distribution of the U's will be relatively centered close to the origin, because this function has a maximum at the origin. Okay, and if you take a function with a zero kurtosis, a Gaussian, and you compare it to a function with the same variance but a positive kurtosis, it will give you a larger value of this quantity. So think about this thing as another measure of non-Gaussianity, replacing the kurtosis that we've discussed a week ago and you're using in one of the exercises. It's some other measure of the probability of a property of the distribution over the U's. I'll show you why this interpretation is relevant to us in a few more minutes. So again, the interpretation now is that we have a linear transformation from the S to the U's. We want to maximize the information of the U's, but at the same time, we have some other goal about the distribution of the U's. We want the distribution of the U's to be more concentrated near the zero relative to a Gaussian distribution. Okay. But again, all Saunderson and Field was a work that interpreted the outcome of the ICA algorithm. They didn't even think about it as ICA. The outcome is mutual information plus sparseness. Okay, but before we go talk about that, I want to talk a little bit about learning rules for ICA. So we found that our goal is to achieve this situation, or to maximize, which is equivalent to maximizing this Lagrangian. But now our equations here are nonlinear, in contrast to the PCA problem. So in the PCA problem, we have it's a quadratic equation. We have a simple equation, and we know how to, using the tricks of linear algebra, we know how to find a matrix that will achieve the goal if it's just PCA. But for ICA, there is no simple way to do it. And this brings up the question, how can we in practice find the appropriate matrix, the appropriate W? Okay. So I'd like to remind you that when we derived the equations that I just wrote, that UI, the average of UI, age of UJ is delta IJ, we used the requirement that the derivative of the Lagrangian with respect to WJ should be 0. And this derivative is given by W transpose, the inverse of W transpose IJ. This is derivative with respect to WIJ minus XI age of UJ. Okay? So one approach to maximizing the Lagrangian numerically is to use what we call stochastic gradient descent. We've already encountered this approach when I discussed the Oja learning rule. The idea is that after each presentation, of a stimulus, we look at the stimulus, we look at the outputs, and we changed our weights a little bit. We apply a change to the weights, which is given by eta times W transpose to the minus 1 IJ minus XI age of UJ. Okay, so this is what we call the learning rate. And if I write it in matrix form, it's delta W equals eta W transpose to the minus 1 minus X H of U transpose. And the idea is that if we pick eta to be sufficiently small, if eta is very small, so the changes in W are occurring very slowly, while we change W only a little bit, we get a chance to sample many instantiations of the input, and so we really sample. We can then replace this discrete learning rule, which is occurring over each step, by the average, delta W, the average change of W over some time scale, where we observe very many different presentations, will really be equal to these the averages here. And therefore, this learning rule, if it's applied sufficiently slowly, will approximate this learning rule, where we have an average over the inputs. That's the idea.
Can you
So the idea again, here we need to perform an average over the inputs, over the statistics of the inputs. We don't know the statistics of the inputs. We're just observing data. But if we observe many, many instantiations of the data, we can average over the statistics of the inputs. Okay? So if we would freeze W for a moment, if we would not change W at all, and we could calculate this expression by averaging over many, many, many examples. So the idea, what we do is, instead of just exactly freezing W, we change W after each presentation, but just a little bit. So there will be some time scale where W doesn't really get a chance to change, so we can think about it as fixed here, but we're sampling many, many examples, and we'll approximate this expression. Okay? Yes, Michael? No, this can be done for any choice of the nonlinear function. It's an example of stochastic gradient descent. Why is it called stochastic? Because gradient descent would be to somehow calculate this and apply it exactly. But when we're observing data, again, we don't know this. We don't really know the averages. We replace this by this rule, which is stochastic, because the inputs are stochastic, right? So, but the notion of stochastic gradient descent is more general. I mean, this is an example. Okay. Now you can see that this learning rule. So in practice, suppose that you receive data, instead of doing what you did you're doing in the exercise using kurtosis, which is a different method. You can imagine applying this method. After each presentation of the data, you calculate the inverse of this matrix. You subtract this thing, and the W's evolve slowly to something. You notice that in each step here, we need to invert the matrix, which is not very nice. So it turns out that there's another learning rule that works as well. Where we don't need to inverse the matrix in each step. So this requires inversion of W, which is just computationally not very convenient. It turns out that the following rule works as well. I won't prove it, but it's possible to show that it also converges to the true solution. The idea is to take this equation and multiply this equation, multiply by W transpose from the left. So instead of applying delta W equals this, we apply delta W is equal to W transpose times this. This is a positive definite matrix, and this is an important reason why this scheme works. This is a positive definite matrix. And let's just see what happens if we multiply by this. Then we get delta W is equal to eta. W transpose times W transpose to the -1 is the unity matrix. So we'll have a W times the unity matrix. And here we will have, again, the W I already wrote here. But what is W transpose times X? It's U, right? So here we'll have U, H of U transpose. Okay? So just turns out that if you take, the data and you apply this rule with a small value of the eta, it also converges to the appropriate solution. And another comment that I want to make is that this rule is not a local rule. Meaning that the change of Wij still depends on other if we think about these as synapses. Yes, it's a different learning rule. It's related to this rule. You saw that I obtained it by multiplying by WW transpose, and it's possible to prove that because this works as well. But it's different. And the advantage is that you don't need to invert the matrix in each step. But if we think about these as synapses from the inputs to the outputs U, if you think about these as synapses and you try to imagine, could a biological neural network apply this rule using some biologically plausible synaptic rules, it's hard to see how to do it. How to apply this rule, because the change in synapse ij will depend on all the other synapses because you have this product of the matrix with this matrix. Okay? So this is not a biological learning rule. It's just a more... it works because this works. This is gradient descent. Okay? Another comment that I want to make is that both these rules are gradient descent rules. They were derived from gradient descent. You're trying to find a minimum or a maximum here of the Lagrangian. It's not obvious that there is just one maximum of the Lagrangian. Okay? And there are cases where there is more than one maximum. So really, if you apply these rules, you are guaranteed to converge on some local maximum, but not necessarily, but there might be more than one maximum. I'm not going to discuss this further, but just keep this in mind. Last comment that I want to make is about pre-whitening. So very often when trying to solve the ICA problem, people apply the following scheme. First, find some matrix, let's call it W hat transpose, such that if we look at X hat, which is W transpose hat X, it will be white. White meaning that the correlation of X hat I, no need for the line here, X hat I, X hat J is delta Ij. So we first apply a matrix that achieves this, and we know how to do this, right? The easiest way to do it is to go to the PCA basis, to the principal component basis, and just squash each direction in the principal component axis, such by dividing it by the square root of the variance in that direction, and then after you do that, you'll get a covariance matrix which is circular, which looks like that. So we know how to do this, but we know also that there is more than one way to do it. So we just pick one way, say the one that I described. Do it in the principal component basis, shift to the principal component basis, and squash each direction. In principle, we could apply after that any rotation. Okay? So this is what you do first. So e.g. rotate to PC basis and multiply a component I by 1 over square root of lambda I. This will achieve this goal. And then the idea is that now apply, after we've done that, apply the ICA algorithm whichever algorithm it is, to the X hats. So basically our U will be some matrix W applied, W transpose applied to X hat, which you can also think of as W transpose multiplied by the initial W hat transpose times X. And why is this initial step very often done? There are two reasons. The first run is that we know that if the UIs are independent, which is what we're trying to achieve, then they're necessarily uncorrelated. Okay, so we've already transformed our x's such that we have. Now remember that we also want our u's, we really care about our u's only up to a scale. Okay? So the idea is the following. We already transformed our inputs x such that they are uncorrelated. We know that the ICA solution must maintain this property. The ICA solution still must, after the ICA transformation, the u's still must be uncorrelated, and therefore this guarantees that we can search for a W here, which is simply a rotation matrix. Because only a rotation matrix, I mean, let's decide, we care about our u's only up to a scale, so let's decide to choose each one of the u's such that its variance is 1. And then, if we want the u's to be with variance 1 and uncorrelated, the only types of transformations that will maintain this property is a rotation matrix. Rotation matrix meaning that W transpose is W to the minus 1. And this is very helpful. Why is this helpful? For example, in the exercise, in your home exercise, where you're using the kurtosis method, you're first searching for one component by maximizing the kurtosis. And then you know, or since you've applied pre-whitening, you know that the next element will be at a projection on a direction which is orthogonal to the first one. This is because you know that the matrix W applied to pre-whitened data, the matrix W will be orthogonal, meaning that its rows and columns are orthogonal to each other. Okay? So it simplifies the search. It constrains the set of W's that you need to search for. There's another reason why people use pre-whitening. And so here the first motivation is that it constrains W to be orthogonal. So in some approaches, it just simplifies the search in that way. And it turns out that even if you don't explicitly use this property, but you apply the learning rules that I discussed here, so in principle, these learning rules will converge if you did pre-whitening or if you didn't do pre-whitening, but they just converge faster. Turns out that they converge faster if you pre-whiten the data. Okay? Okay, next I want to show you some plots. I think that I'll finish a bit later. You'll take a regular break, and maybe the Tirgul, the TA, will be a bit shorter. But I just want to finish this. So now I want to talk just very briefly about receptive fields in the visual cortex. Around 1996 and 1997, there were several very influential works, mainly by two groups, Olshausen and Field and Bell and Sinofsky, which came up with some principled with some optimization principle that they claimed explains the receptive fields in the visual cortex. I remind you that the receptive fields in visual cortex are not center surround as in the retina. They have their functions that are oriented, a little bit oscillatory, what is called similar to what is called Gabor functions. And there were two lines of work, one by Olshausen and Field. And what Olshausen and Field said is that the transformation from the visual inputs to the outputs of the to the representation in the cortex maximizes entropy or mutual information. It's the same if there's no input noise, plus sparseness. If you read their paper, that's what they say. The goal, the principle at work in the cortex is maximization of entropy plus sparseness. But based on what I've told you earlier today, you can reinterpret this idea as independent component analysis. They didn't really realize this. Another set, a different work by Bell and Sinofsky claimed that what the visual cortex is doing is Infomax maximizing some the entropy of G of U, right? This is the way we describe the Infomax approach to ICA, and they also pointed out that this is equivalent to ICA, to independent component analysis. And let me just show you a few plots from both of these works. Okay, so this is from the Olshausen and Field paper. They showed that after they search for a set of receptive fields that, they took patches of natural images of, I don't remember how many pixels, not that many, patches of natural images, and then they applied to them some stochastic maximization gradient descent algorithm that maximizes entropy plus what they call sparseness. And these are the receptive fields that they got. And they look much, much more similar to, they qualitatively look quite similar to receptive fields that are observed in visual cortex. One thing that is a bit difficult for you to see here, but is true, is that first of all, it's easy to see that there are that these things are typically oriented. They have some spatial frequency.
What does that mean?
So this is this means actually these. Okay, so what these are the independent components of the visual scene. Okay, but this is related also to the receptive fields. If you ask what is the linear relationship between the output of a given unit to all the input units, this is not what is shown here, but it looks very similar. Okay, so and this is what we would call the receptive field of a neuron. So you see that you see all different orientations here. And in fact, there is also a range of spatial frequencies. It's a bit more difficult to be sure about it from looking at this plot, but it's true. And all these observations are qualitatively similar to what is observed in visual cortex. And you see here, what they show here is the distribution of the output units after they apply their algorithm. You see that it's more sparse, it's more centered around 0 than the initial distribution. Very similar idea was obtained by Bell and Sinofsky in their work, where they applied explicitly this algorithm, which is related to ICA. But again, as I showed you, these two algorithms are really very, very close in what they're doing. And again, they got some very similar results. And this is just to show you that this goes beyond the visual processing. This is a paper by Michael Levicki. This is from the 2002 paper, where he claimed that if you take recordings of natural sounds, and he actually combined natural sounds and more and also sound like things like speech and animal vocalizations, and do a independent component analysis to them, you get independent components that are very similar to the filters that are applied already at the level of the auditory nerve. So this is a bit different from what we see in vision. In vision, the output of the retina is not doing independent component analysis. It's generating something which is, we motivated it by principal component analysis, decorrelation, plus the notion that the receptive fields have to be all shifted versions of each other, and only at the cortex we see something that looks like the outcome of independent component analysis. For audition, the claim of this paper is that if you record on the on the auditory nerve, which would be like recording from the output of ganglion cells, you already see something that is, so these are these examples. These are the filters applied relating the output of a given auditory output to the natural sound. This is in the time domain. And you see that these filters have this structure that are localized functions in time, but with some oscillation. And very similar to the functions that you get here. If you read more carefully what they write, they say, actually, if we take natural sounds, this is what we get. If we take animal vocalizations, we get something that looks completely different. If we take human speech, we get something that also looks a little bit different. And to get something that really looks a distribution of filters that is very similar to what you've seen in the cochlea or in the auditory nerve, you need to assume that the input statistics are some combination of natural sounds and these sounds. But at least qualitatively, it seems like this ICA principle can explain the qualitative structure of the receptive fields. Okay, I will continue for 5 more minutes. I just want to wrap up this discussion about independent component analysis in the context of processing in the brain. I mean, we discussed it mainly as a signal processing problem, in a sense. We want to separate sources. But towards the end, I've shown you that if we take these ideas, they qualitatively give us a good prediction for the structure of receptive fields in various sensory areas. But now what is the interpretation? Here, it's much less clear. I mean, if you look at different papers, they say different things. Maybe the goal is sparseness, okay? Maximize information, but for some biological reason, it's good that cells in the visual cortex are sparse, whatever sparse means. I mean, sparse is defined by this term in the Lagrangian that I wrote earlier today. Maybe that's beneficial. Maybe the goal is infomax in this sense, but then you need to consider the specific form on the nonlinearity. And it's really not clear whether the nonlinear properties of cells in the visual cortex are set such that they are the cumulative distribution functions of the input statistics. It's not even so easy. It's not even very easy to ask this question, because in contrast to our model, cells in the visual cortex are spiking neurons. They're not just analog outputs. They don't apply simply an analog input-output function. Maybe the goal is simply related to efficient coding downstream of the visual cortex. This is what Bell and Zenovsky hypothesized. Maybe it's not efficient coding, but maybe the goal is really to identify the independent components of the image. Maybe it's beneficial for visual processing to represent, not for coding, but really for the computations that one needs to do on to perform various visual tasks. Maybe it's beneficial to shift to a representation which is closer to independent components. Now, we don't really think that true natural images are generated by independent components which are Gabor filters, but maybe it's a close approximation. And indeed, in computer vision, it has turned out to be very beneficial to first transform to a representation that involves the Gabor filters. but even this is not so clear. Is this because it's a fundamentally good way to process natural visual scenes, or is it because the tasks that we require from artificial system are similar to the tasks that humans do, and humans use this representation? So maybe this is why it's useful to shift to this representation. And so let me just mention two main questions, which I think we have hints about them from all the works, but not a very clear picture. First, do sensory areas perform ICA? So in vision, we have some indication that it's true, also in the auditory case. Another sensory area where this would seem to be the most natural thing to do is olfaction, because in olfaction, we indeed have sources which are odors, which are some mixture of sources, and the way we sense the odors are by the way that they stimulate the different olfactory receptor types. So it's a really like linear transformation, mixing the different sources. It makes sense that in olfaction, the brain would apply something like the independent component analysis, but the answer, whether this is true or not, is much more elusive than in the other senses, in auditory and vision. Do you know why it's more elusive for odors? No. So the answer has to do with the statistics. For images especially, but to some extent also for auditory stimuli, we have a good notion of what is natural statistics. For odors, it's much, much less clear. So the statistic, the space of different odors and its natural occurrence statistics is much less characterized and clear. And this is why it's much more difficult to answer whether the representation in the olfactory system is somehow shifting to independent components. So this is one set of questions. Whether at all the brain applies independent component analysis. Again, there are some hints that this is what is going on, but maybe it's not exactly because, maybe it's because the brain wants to generate independent component. Maybe it's because of some other reason. And another interesting question is that of learning. So I've shown you that there are some learning rules that generate unsupervised learning that generate the ICA representation, but they were not local learning rules. Okay, so it's hard to imagine these rules applied in a neural network, and this raises the question whether there are more biologically plausible ways to do it, or maybe in some cases it's just hardwired in the connectivity in the brain. So all these, I'm not answering any of these questions. I just want to provoke your thinking about this, and we'll take now a break. We'll have a short RTA session afterwards. Okay. Actually, you know what? Even shorter. I shorted it by 2 more minutes. I just want to point out that this was the original plan for the course, and we did this. When we did this, we're here, but instead of being after week 4.5, we're after 7 weeks. We have exactly 7 more weeks. So we're going to. I wanted to really talk with you about this topic, which usually hasn't been taught in this course, but I'll have to skip it. Please note that you have a hole in your education. You need to understand how do people characterize receptive fields of neurons in reality based on measurements from neurons. It's an interesting topic. There is some interesting theory behind it. But we will skip directly to this topic, neural decoding. And then this is another topic that I thought that I will add, but no chance. So after that, we'll skip it and we'll go directly to supervised learning. So this is the plan for the next 7 weeks. Okay.
שאלתי עכשיו מה זה, שאלתי נלמד מה זה.
לא יודעת מה צריך. אם אני אגיד לך מה זה, תבין שאתה כבר יודע מה זה, אוקיי? מה זה ICA זה שאלה הרבה יותר מורכבת, אני גם אגיד עכשיו, זה לא אלגוריתם אחד.
כי לא נראה לי יש ממש מושג מה הולך פה.
אני PC אני הבנתי, ו-ICA לא הבנתי.
כן, סבבה, בסדר. כאילו בעיקרון ICA
אז התחלת בגבול?
אף אחד לא נמצא, לא. לא, אני רק אומרת, אני כאילו, לגבי ICA זה הגיוני שאתם לא מבינים מה זה, כי אין, CCA זה אלגוריתם יחיד מוגדר היטב, זה רישום של המטריצות קובלנט. זה דבר מאוד ברור ומתמטי שמוגדר מה זה. ICA זה לא. ICA זה למצוא את ה-independent component, שאין כאילו סכמה כללית שתמיד עובדת לכל התפלגות למצוא אותם. אנחנו נותנים פה מקרים ספציפיים, שתחת המקרים האלה אנחנו אומרים איך אפשר למצוא את ה-independent component במקרים הספציפיים האלה, אבל זה כאילו לא משהו שאפשר...
מה היה ספציפי? הוא לא...
אז מה שיורם עשה בכיתה זה שהיה נגיד כמה מקורות בלתי תלויים, עשינו טרנספורמציה לינארית שלהם, ערבבנו אותם, ומתוך התצפיות על הערבוב של ה-independent component, אנחנו יכולים לחזר מה הם היו, כן אמרת אפשר לעשות את זה. ותרגול עכשיו אני אתן דוגמה אחרת.
ממש אנחנו לא מנסים לשחרר, כי באותה תשגיח.
נכון, לשחזר עד כדי למתוח אותם, אבל...
לא, הייתה פונקציה לא לינארית על התצפיות.
מה?
הייתה פונקציה לא לינארית על התצפיות, שכאילו... שניסינו למקסם את האינפורמציה.
נכון, זה היה בשביל כאילו...
אני לא הבנתי, למרות ששאלנו את יורם שבוע שלך והשיעור מסביר את זה,
אוקיי.
כל המוטיבציה לעבור ל-G Y.
בגלל שהם...
מה שאנחנו באמת מתאמנים בו זה בדיוק, נכון? זה מה שאנחנו...
נכון.
ומה אנחנו צריכים
ומה הוא בסיס את G?
G זה כאילו הפונקציה הלא לינארית.
למה בכלל עברנו ל-Y?
אני צריכה, אני פשוט את יותר, אני לא זוכרת מה זאת הייתה, אז אני צריכה לקחת שתראו לי לראות.
בחיי? אז איך אמרת על השאלה הזאת? כל מה שקורה בחיים שלי? בגדול?
לא, מה אפשר להגיד? לא כל,
בקורס הזה או בכלל?
בכלל, בלימודים.
בלימודים?
לא יודע כמה. זה בעצם כל החיים.
שמה?
זה בעצם כל החיים. כל החיים.
שלי? שלי לא.
עד 4.
שעות?
יאללה, נוכל את כל העוגיות לפני שהם באים?
אני רוצה שנה הבאה גם להציג פוסטר.
מה?
אני רוצה שנה הבאה גם להציג פוסטר.
זה טוב.
כן?
כן, זה ממש טוב. אתה מקבל מלא רעיונות והערות שכל פעם לא...
איך את מחלקת את החיים שלך לפני שהצגת פוסטר? שלשום ואחרי.
אז אני מתקדם לפני שעברתי את חיים, כדי לראות פוסטר שלי אחרי.
האמת שבאתי להקשיב, לא רציתי לשמוע. אבל אז כאילו אני מבין. חיים כבר, דיברת עם חיים. כאילו אני לא ברמה של זה.
יאללה, אולי תעזור לי בסיבוב. מה אתה עושה? בוא נעשה שיעור עדיין.
אני רק רוצה לסדר את ה...
נגמרת? רגע אחד.
הייתה הצעה אחריי? דלק נתן.
אני לא אוכל להגיד. מה, את עכשיו מתחילה?
הולך מחר לכנס?
יש לי תור לרופא בבוקר ואז יכול שאני אתחיל. אתה הולך?
נראה לי. אני גם אפילו לא יודע, כי אמרו שיש פה את מישהו הזה בוויצמן.
בחמש.
את הולכת?
למישהו בטוח, כן.
גם אני, אבל זה too much.
נכון. כן, לא יודעת מה להגיד.
את האמת, הגעתי לשורה שנייה ולא הצלחתי להמשיך.
דווקא נמרוד אמר לי שרציתי שהיה לו לא כי מהמחזורות. דווקא ידעתי לו הצליח לך.
בטח פרסמתי, כאילו?
פרסמתי אבל הייתה בעיה במודל ואתם לא רואים אותו. עכשיו בגלל זה שרק היום היה לי באג שאתם לא רואים אותו, אני יודעת שלא נורא
אנחנו פשוט חיפשנו אותו ששענו.
זה לא חסובת להרפחות. בגלל שלא נראה לי שזה היה הרבה לחץ עליו מהמשפט. בגלל שלא... מיום ראשון זה היה מראה שיש בעיה, אף אחד לא הפסיק כאילו בגלל.
תהיו בעד.
סבי זה סידרתי את זה.
למה שלא הגעת לספר?
עוד פעם, איפה מאוחר כזה?
Okay, so today we're going to do a question that appeared in Moed Aleph last year to conclude the subject of F5CA. So before we're going to solve this question, I just want very briefly to say a few words about PCA and ICA. We talked a lot about it until now. So PCA is Principal Serial So PCA is something that is well defined, and actually we did it a lot until now. It's finding the principal component. It's just finding the eigenvectors of the covariance matrix of the data. Okay, so for any kind of data which is given to you, you can always diagonal the covariance matrix, find the eigenvector, and then you will get uncorrelated components of the data, right? And for Gaussian, the uncorrelated component will be also independent, okay? But you can do it to any kind of data, and people do it a lot in data analysis, not only here. And the ICA is what you talk about now with Iran, is find the independent regarding to ICA is what you're doing now in the lecture. So for ICA, there is no general scheme that will always work, okay? So PCA is something that is well defined. You can do it to any kind of data, but ICA is something different, and for different types of data, there are different algorithms to find the independent components. And in this course, we just give you a few examples, but this is a huge field, and if you want to use it when you do data analysis or things like this, you should learn more about that. But in this course, we give you specific examples for doing ICA, okay? And now I want to move to the questions from the exam last year, okay? Any brief question about that, because it's not the subject now, we can go on. Okay. So we don't have a lot of time, and this is a quite long question with a lot of algebra. I'm not going to do here all the details because we don't have time, but I want to talk more about the method and the idea of this question, and all the algebra will be in the Moodle later. Okay, so don't be nervous if I skip some of the algebra stuff. Okay, so okay, so in this question, we have two sources of data. First, I will plot it, and then I will write automatically the terms. So we have two Gaussians, the green Gaussian and the blue Gaussian. Okay, and
Like points.
this is points. These are points. And the data is come from the following probability function. Okay, so what we have here is
What are the direction there?
this is the R1, R2. What's that? Okay. So the idea is that we have two Gaussians. We have probability alpha to choose Gaussian A, okay? Probability alpha to choose the green, one of the green dots, and probability 1 minus alpha to sample a point from the other Gaussian. So first, we just choose randomly one of these Gaussians, A or B, and after we choose one of them, we sample a dot according to his distribution. Okay, so this is not like what you had in class. What you had in the lecture was independent components, but then we did a linear transformation. We somehow sum over the independent components, and this is not summation of two Gaussians. Okay, it's just mixture of two sources that we can either sample from this one or either sample from the another one. But what we see, but what we have is all these dots, and we don't know which came from which of them came from which one of the Gaussians. Okay.
What is R1 and R2?
It's just the axis.
But in the probabilities,
The probabilities are
like you call it R1 and R2.
is vector, sorry. Okay. Okay, so our goal was given all the data, given all these points, we want to reconstruct the principal axis of the original Gaussian. Our goal will be to find this axis. Okay? Alpha is the probability to sample from the Gaussian A. Is a number alpha is between 0 to 1. Is the probability to sum from Gaussian A. R1, R2, and we want to find W such that S1, S2 will be the principal axis. איך כותבים axis כאן? of the original Gaussian. Okay, is it clear? Is it clear what you want to do? Okay, good. So first of all, step one is to find the S's is just the output. S's is I define the output to be S. The output is the linear transformation, is the new axis actually. Okay, R1 and R2 will be the new axis in which we want to represent the data. Okay, now
S1, S2,
it will be the, yeah. Now the data is represented on the axis of R1 and R2. Okay, and S1, this is supposed to be S1 and S2. Okay, the axis the new representation of the data. Okay, is it clear?
It's not clear if this is PCA or ICA or if it's the same thing but it's a Gaussian also.
No, it's okay. It's not PCA. This is ICA because the two Gaussians are independent. Okay, and we want to reconstruct the. You write that this is the principal component of each of them, so it sounds similar to PCA, but we're not doing PCA to the whole data that we have now. Okay, because doing PCA it means to any kind of data. If we do PCA, we just find the principal, the eigenvectors of the covariance matrices. In this case, they can be something completely different from S1 or S2. They can be something like this or something like this, independent the variance of the data. It's not necessarily will be the main axis of the original Gaussian because you see all the points together, not only one of them. But we can go over it later because it's an important point, but I really don't have time now. But I will explain you later.
Given that they are independent?
The original, yes, because the way which I define it here is I use a sample from this one and from this one, and each of them is independent by the other one. Okay, let's go on because we don't have time. But I will explain it later too because important point. Okay, so first of all, we want the covariance matrix of the data, and it will be 1. So I will not show you, but it's possible to see that the covariance matrix of the data C is equal to alpha CA plus 1 minus alpha CB. Okay, that should be easy right now, but it's quite easy to see, to do the algebra and to get it. It's not a guess or something. So now in order to find the principal component in which we are looking for, we will do now 2 steps. Okay, this is the main step for solving the problem. So we are looking for data for axis in which the representation over this axis, the data will be independent. S1 and S2 should be independent. So a necessary condition but not sufficient for independence is that S1 and S2 should be also uncorrelated. Right? Independent, it means that all the moments So if I would just make them uncorrelated and take the largest axis, it will be like exactly like doing 58. If I will stop at this moment, at this second moment, but we're looking, but here it will be only our first step because we're looking for independent data and not only uncorrelated data. Okay, but to make the data uncorrelated isn't necessary in order to do the CCA. Okay, is it clear?
But if both of them are Gaussians, then wouldn't it be the same if they're
No,
uncorrelated?
because the data that we have here, this is not a Gaussian. It's different. It has this shape, right? This is not a Gaussian anymore after we did the mixture. Okay, because it's not linear summation of a Gaussian that like we had before. It's a mixture of two Gaussian, something else. Okay, so there are many ways to make the data uncorrelated, and we will choose. So 50A is the one way to make the data uncorrelated. We choose the principal component of the covariance matrix, but we can also use different method. It's called whitening. Yoram mentioning it in the lecture. So that time will be whitening the data. Okay, so whitening, it means that we are looking for W such that S transpose will be the identity matrix. This is meant to make the data white. Okay, it means that under the transformation that we will do to R, the output will be uncorrelated, but also the variance will be the same on each axis, and that's what we told you how does it look like, okay?
It's
So
constant multiplied by I, right?
uh-huh.
It's constant multiplied
Yes.
by I.
Yes, you're right. Exactly. But in this case it's also an important point. We don't really care to למתוח את הצירים. To stretch the axis. Okay, I just want to find the direction. So I don't really care what is it, okay? But this is one that I don't okay, so whitening, I'm showing you now an example. It's not this case, okay? Just for you get an intuition what is whitening. So if, for example, I have a Gaussian and I want to make it white, so first I transform into the principal component of the Gaussian, and then I just shrink the axis in order to be also a circle. Okay, so now the variance is the same in all the directions. Okay, so under this representation the data is uncorrelated, but more than that, the variance is symmetric. The variance is symmetric in all the directions. Okay, that's what we want to do also here to X, to the output. Okay, so a general scheme to widening the data. This is like I will write you how you should do it. Okay, this is only an intuition.
Initial step leader to the solution.
At the end, yes.
How?
No, we have more steps. This is only the first two steps. Okay. Well, later we'll move on to the step three, and this will be the solution.
Step 3 would take uncorrelated to independent, or?
Yeah. Yes.
But didn't Yoram say that we can do correlated also?
Yeah, but we can. But again, this distribution that we have here is not Gaussian distribution Gaussian, and then you do a linear transformation to it, y equals to ax, then you cannot reconstruct x, because y is Gaussian, okay? But here, our y is not a Gaussian anymore. So that's the reason that we can reconstruct the original problem. It's not a summation of a Gaussian, like in case of like for example, if it was one dimension, so if this is one Gaussian and this x1 and this is x2, how the summation looks like is something like this, okay? This is x1 plus x2. This will be the summation. But in our case, so the new distribution would be something like this. But in our case, the new distribution is this. This is our new distribution. It's not Gaussian distribution. The new distribution that we got from the mixture. Do you see the difference between sum over two Gaussian variables and to mix them? So this is like if you sum them, then you get Gaussian. But if we mix them, we don't have Gaussian anymore.
So we can't use the
So we can use.
No, I mean we can't use the first method of
No,
that
no.
was because we in the preceded one process we need to find the
Yeah, it's something else than what Yoram did. It's something completely different than what we saw in the lecture. Okay? Yes. In the lecture, it was a summation of data, and then we have mixture of data. It's different things. Okay? Okay.
Can you conclude if you mix them? If you mix two Gaussians, you cannot reconstruct?
No, if you sum over Gaussians, you cannot reconstruct the original.
And if you mix them, do the combination like
It's not like in this case you can. I don't know if it's something that is true in general.
You mean them?
The whitening step, what do we, I mean, in one step that define, what's the difference?
I didn't get to it yet because I will show you now how we do it, okay?
Is this a requirement?
I didn't show you. This is a requirement. Yeah, yeah. Right. Okay. So what we do in order to get the white data is okay. So if say if so if this is the decomposition of the covariance matrix, I can do the whitening by the whitening transformation will be W equals to lambda to the power of square root U transpose, and I can always this is a general way to, if I will take this matrix and multiply the data with this matrix, it's quite easy to show that you get the desired, that you will get this, okay? No, and this, okay, and you can always also multiply this by an orthogonal matrix, okay? Because after the data is white, is circle, we can always rotate the data and the data will still be white. Okay, so this is one way to do a whitening, and we can always.
What's W again?
W is the matrix, so S is to the data R in order to get, and C is the covariance of R. Okay, is it clear? No.
Why is that the last information?
You can just substitute it, calculate S and transient, and you receive, you get the identity matrix. That's algebra. I don't have time to show it to you, but believe me that if you take this matrix, you multiply it by R, then, so if I take, so now if S is WR, then SS transpose is proportional to the identity matrix. Okay? I think now it will be equal to the identity matrix, not proportional in this case. Okay? Or still, you can just substitute it and you will see. Okay? But lambda is the eigenvalue matrix of the, and U is the eigenvector of the covariance matrix. Okay? And I think that you will show it you should show it in the exercise, but it's quite easy. Okay, wow. Okay, so I tell you that this is a general form to make the data white, but actually you can multiply the data, the white data, by any orthogonal matrix, and the data will stay white. בואו תגידו לי כי זה חשוב, מה לא מסתדר? Sorry, what's the problem? מה?
We're having a hard time seeing like the big picture and what we're.
Okay, so the big picture is if you want to reconstruct S1 and S2. Okay? Now, one of the steps in this process is to make our data white. In the next step, we will also reconstruct back the S1 and S2, but before we're doing it, we just need to make the data white. An intuition for that is that whitening means that S will be uncorrelated, okay? And maybe in a few minutes it will be more clear why we are doing it, okay? And if not, just listen, because this is important. The big picture is important.
Also, is it plus or minus half?
Sorry, minus half. Okay, so after I'll just write it to you. After the whitening, we can multiply the two data by any orthogonal matrix. And the data will stay white. The data okay, so here I gave you a general way to make the data white, but then you can also multiply it by any rotation, by any orthogonal matrix, and the data will stay white. Okay, so now see here that we have many ways to make the data uncorrelated. Any rotation of the whitening will keep the data uncorrelated, and therefore I can choose any direction of the rotation in order to get the optimal solution. And in this case, I will write it to you. We're looking for the rotation that will maximize the sum of the kurtosis of the output. Okay, I will write you what does this mean, what everything is said now, but so now we will assume that alpha is equal to half, okay, that this alpha, the probability to sum from this one and from this one is equal. So assume, okay, so in this case, so where alpha is equal to half, the general form of the whitening matrix is just a rotation. It's just a rotational matrix. In this case, the whitening matrix and we want to find theta. I will go over it again now, okay? I want to find theta. That's that. K till S1 plus K till S time will be maximal. Okay, so
K.
K is the kurtosis. Okay, K is kurtosis.
It's because we assumed S1 and S2 are bigger when it goes from third to the third?
Yeah, so okay, so we have maybe two steps here. So we said that the one step is making the data uncorrelated. We do it by whitening. I gave you the formulation for how we should find the whitening matrix. And if you substitute if you solve it and find the eigenvector, the eigenvalue for the case in which alpha equals to half, you get that this is the shape of the whitening matrix, okay? In this case, I'm not showing it you how, but just believe me that this is in order to make the data white, you just need to rotate it by an arbitrary angle. And now we want to find before I gave you the shape of the whitening for general, if you substitute the eigenvalues and the eigenvectors, you will get the whitening matrix for general alpha. But finding the independent component for an arbitrary alpha is more difficult than this case. This is very simple test. I'm not going to do the harder.
In the original question, do they tell you to assume alpha is half, or are you supposed to not?
In the exam?
Yeah.
No, they tell you.
No, I'm just...
Yeah, they tell you that. Okay. So we don't have a lot of time, so now I told you that we want to choose the rotation that maximizes the kurtosis, and just an intuition for why do we want to maximize the kurtosis of the output. So you can see that in the principal axis, the kurtosis is very high here, right? The distribution looks something like this. Okay, so this is just an intuition why under this representation the kurtosis of S1 is high. High kurtosis distribution somehow. Yoram defined it in the class exactly what is kurtosis, but if you remember the definition, you can see that you can understand why the kurtosis under this representation will be high, and this is an intuition why maximizing this kurtosis will give us the desired result. In the exam, they told the students that they should maximize the kurtosis. They didn't ask them to find the optimal ICL algorithm. Okay? They asked them to maximize the kurtosis. So is it clear like what is the main approach here, or not at all, or not at all for now?
You
Yes.
maximize under constraint, under what?
Maximize here, no, it's not. It's find the theta that will make that will maximize this expression. Okay, so we can the shape of this expression is known. So we know what are S1 and S2. S1 is
If we widen the data, so are the variances equal on all
on all directions.
so how can we
How can we choose which direction we want?
no how can we maximize the kurtosis if the variance is equal in all directions?
Because